this series of Snap Circuits videos, we're looking at Project 258, which is the fan modulator, and we're going to project number 271, the light-activated burglar alarm. So, again, we're looking at Project 258, which is the fan modulator. There's what it looks like in the book, and we also make this little disc here, 3 inches in diameter with kind of a little cutout there. I've actually taken a wheel from an older project and cut a notch out in it to do the same effect. So on the board here, we're using our 3-volt source with our 2.5 volt lamp connected in series with our motor, which of course has got our modified disc, and that's controlled with our press switch. While down here we've got an NPN transistor with its gate being fed by the variable resistor, and it's controlling our red LED here and then turning the circuit on and off for that entire thing with the slide switch. So if we turn on our slide switch, nothing happens right now. We keep our variable resistor toward the middle there, but we take out, if you have enough ambient light this will work, but I'm going to use an ultraviolet flashlight here. We're going to hold it over the top there, and then we're going to press the press switch so that we can make our motor spin up. And you see as it spins up, our LED flashes there, and we get a little bit of illumination on our 2.5 volt lamp being connected in series with the motor there. And you see as our disc is turning over here, that opening is passing over the photoresistor. That's the one thing I didn't mention there that's also controlling our NPN transistor here. And every time that notch passes over it, the light from the ultraviolet flashlight here comes through, striking it, which allows it to provide enough current to the gate to turn on our LED. And because it's a notch, it's basically modulating the LED. That's why they call it a fan modulator, because we're controlling the LED's brightness or luminescence by turning it on and off through the control through the photoresistor here. So down steps. And we can turn it on again, make it start flashing again. And again, if there's not enough ambient light, it's not going to work. So that's why I'm using this light here. You just see the LED is being controlled by the light there. So that is project number 258. Now project 259 that we're going to look at is an oscillator. And here we are with project number 259. This is the oscillator from 0.5 to 30 Hertz. There it is in the book, and then there it is on the board. And so here we're making use of a couple of capacitors, a couple of resistors, our variable resistor, including our PNP and NPN transistors. So we kind of got this Darlington transistor set up again, and our output is our red LED. So when we turn on this circuit and you keep your variable resistor slider all the way to the bottom, when you turn the circuit on, the LED starts flashing. And it's flashing at a rate of once every 2 seconds, or 0.5 Hertz, as what the book says. And you can probably guess if we adjust our variable resistor, we can adjust the rate at which that flashes every second. So that's why it's 0.5 to 30 Hertz, because we can adjust the frequency or hertz that our LED is flashing at, basically controlling the frequency in our circuit. And eventually it gets so high that it looks like the LED is on all the time to our naked eye, even though it's actually flashing really fast, 30 times a second. And we can continue controlling that by bringing it back down. So that's probably about 5 Hertz there or so. Maybe getting up around 8 to 10 Hertz there. And then it gets up pretty quick. We're probably about 15. And then we're up to 30. So this allows you again to control the frequency or oscillation in the circuit. To control how the rate of that LED flashes. Now, Project number 260 is the sound pulse oscillator. For that, we're just going to take our speaker with a 1 snap and we're going to put it over top of the LED. If I can get it on there. There we go. And now, you can't see the LED, it's still blinking, just not as bright, but now the speaker allows us to hear the oscillation in the circuit there. And just like before, we can take a variable resistor and we can bring that frequency up. So that's how projects number 259 and 260 work. Now we're going to move on to 261, which is Motion Detector 2. So here we have project 261, the Motion Detector 2. There it is in the book, and here it is on the board, slightly modified, since this is a 6-volt circuit and we're using our battery eliminator. So we have our NPN transistor and its base or gates being controlled via a variable resistor, but also our photoresistor as well, which controls our red LED through our 1000 ohm resistor. So we have our variable resistor all the way at the bottom. We're going to turn the circuit on now. And with it set right now, there's just not enough going to the base here to turn our LED on through the transistor. So let's move the variable resistor all the way up, and as you see now the LED is nice and bright. We'll bring it back down, and it will go off, and bring it up to just where it turns on, to about there. So it's stimulated, and as we take our hand and move it around our photoresistor, of course, the photoresistor also changes the amount of current going to the base of the transistor there, depending on how much light is entering it. And because of this, we can effectively turn our LED on and off. And of course we can control how much that goes, but we want it about here, so that when it's covered up, it's off. When it's uncovered, it's on. So that's how project 261 is. Now project 262 is motor rotation. So here we are with project number 262. It is motor rotation. There it is in the book, and there it is on the board. And here we're using our two 3-volt battery boxes opposite of each other, and our motor is in the middle, connected with our 2.5-volt lamp and our 6-volt lamp in series with it to act as current reduction, and then we control it with our slide switch and press switch. So we'll use our press switch. You see that our fan turns clockwise, and we get a little bit of illumination on our 6-volt lamp there. If we come over to our slide switch and turn the slide switch on, you see that now the fan turns counterclockwise, and we get a little bit of illumination on our 2.5-volt lamp. So what's happening here is the polarity on our motor is changing depending on which switch we've got enabled here, based on how it's set up with these batteries. If we're using the press switch here, see, positive on the battery is right here. So what's happening with this is our current is going in a loop like this. And with the current going in a loop like that, that makes our fan turn clockwise, because also the positive terminal of the motor is up top here, so it's in line with the battery. Now if we use our slide switch, our fan turns counterclockwise because positive of the battery is here, so our current is now flowing in a loop like this. See, our current is flowing this way with this side, while on this side the current is going like this. So you see how the polarity changes there depending on which slide switch we use, because this is reverse polarity and this is normal polarity when you look at it on the motor there, and because of that, that determines which way the motor rotates. It can rotate clockwise or counterclockwise. So that is project 262. Now project 263 and 264 is our motor delay fan. So here we are with project number 263, the motor delay fan. There it is in the book. And there it is on the board. And one thing I noticed here is they've got the positive of the motor to the negative of the battery. For this, I've actually reversed this so the positive is over here so the negatives are together, because otherwise the fan here will actually fly off the motor when it stops. So a little something you might want to consider if you do that. So here it is on the board. So we're making use of our two transistors again with our Darlington setup, the PNP and NPN. We have our number 4 capacitor here, and also we have the, of course it's a 100 microfarad capacitor, our press switch, and our slide switch, that general circuit. Of course we talked about the motor, and our variable resistor. So if I bring the variable resistor all the way to the side here, let's turn our circuit on. When we press our press switch, the motor comes on, and if we let it off, the motor comes to a stop. Now if I put it about to the middle here, let's try again, the motor spins up. But when I let off the press switch, the motor continues to run for a little while, and it gets slower and slower until it stops. And then I can move the variable resistor all the way to the right here. Power up our circuit again. And when I release the press switch, the motor stays on even longer now. So why is this happening? Well, this 100 microfarad capacitor here is getting charged up when we press the press switch, not only turning on our motor, but also it's feeding the base of our NPN transistor there, allowing it to keep the transistors on to allow the motor to run until again it completely discharges, and then it can no longer keep the transistors on to the point where the motor no longer runs. So with project 264 we modify that a little bit, and we've already put a 1 snap on here. We take our 470 microfarad capacitor and put it over top of our 100. Now parallel capacitors, which is what we got here, and add together, so we have 570 microfarads of capacitance. So if I put my variable resistor over again and try this circuit once more, again the fan stays on for about the same, because the capacitors discharge quickly through this side of the circuit versus the base with the variable resistor set here. Put it about to the middle again. Power up our circuit and charge our caps. And now the fan is staying on for a longer duration because, again, we have several times more capacitance than what we had before, putting that 470 on top of the 100. And so by that, our fan stays on longer. Getting slower and slower as those capacitors discharge. And that's it. So by playing around with our variable resistor, we can adjust the rate of how much the capacitors discharge, and depending on that setting, we can determine how long the motor stays on after we release the press switch. So that's projects 263 and 264. The next one will be 265, which is our high-pitch bell. So here we are with project 265, the high-pitch bell. There it is in the book. There it is on the board. We'll also have projects 266 and 267 here. So we've got another oscillator circuit with our speaker acting as our output, along with our whistle chip, 2 resistors, our PNP and NPN transistors, along with our red LED, and 6-volt lamp. So when we press the press switch, our red LED comes on and we get this squealing sound from the speaker, because the circuit begins to oscillate, so it kind of starts off and kind of gets to an equalization point where it stays constant. You know, my press switch is still a little funky. I haven't quite replaced that yet. But you get the idea of how the circuit works now with 266, the Steamboat Whistle. As some previous projects with oscillating circuits with frequency sounds like this, we're going to use our capacitors across our whistle chip to lower the tone or frequency and generate a lower pitch sound. So this is capacitor C1, our 0.02 microfarad. We put that across the whistle chip. Now they think it's supposed to sound like a steamboat. See, it's a lower pitch sound now. As before, where we had this sound, we put this across it, and of course that lowers the pitch down. Now project 267 is the Steamship, as they call it, and you might guess we're just going to take our other capacitor, 0.1 microfarad, and put that across the whistle chip. Now the sound will be even lower in pitch. So just like with the other ones, it starts off with a high pitch, and then we put that on there, and we bring the pitch way down because we've got more capacitance across that whistle chip. So that's projects 265, 266, and 267. Now as a little bonus here, they don't have it in there, but in the previous project we've used our 10 microfarad polarized capacitor across the whistle chip. And what do you think happens when we use it on this circuit? See, we get kind of a pulse or a beat. You can see our LED lights up brightly. We actually get illumination on our 6-volt lamp, and you hear the pulse through the speaker. I'd say it's probably equivalent to a heartbeat at a certain BPM when you think about it. But that's just a little extra making use of the circuit with our 10 microfarad capacitor, even though it doesn't call for it in the book, but we've done that with previous projects like this with oscillating circuits. So now we're going to move on to project 268, which is the light NOR gate. So in this video we're looking at project 268, the light NOR gate. And I've actually done an entire video using snap circuits on the operations of logic gates like AND, OR, NOT, XNOR, NOR, things like that. But this one's in the book. And basically what we have on our board here is our 3-volt source with our 2.5-volt lamp being run through our NPN transistor, which is being turned on by resistor 2 here, our 1000 ohm resistor. And we have our slide switch and our push button switch acting as our conditions that represent true or false. So right now, in this state, it's considered true because we have 2 false statements here. The slide switch is off, the press switch is not pressed. But we have a true statement because our 2.5-volt lamp is on. Now, if we turn on our slide switch, that lamp goes out. So now we have a false output on here. So this is true, this is false, thereby our output is false. If we also press the press switch down while holding down the switch, well, now we have 2 true statements, but we still have a false statement coming out of our transistor there for our lamp because it's still off. And of course, if the press switch is on, well, this is false, this is true, but that's false there. And then of course, if they're both false, well, now it's back to true. Because what's happening in this circuit is when we use the press switch or our slide switch, we divert the current away from the base of our transistor here. Instead of going through the transistor like so, it ends up going through around like that, and that cuts the flow off to our transistor so it doesn't turn on and thus our lamp goes out. So that's how Project 268, the light NOR gate, works. Again, I did a whole video on logic gates and their operations, which I'll probably reference in the description or maybe somewhere up here in the video to look at if you want more into that. So now we're going to move on to Project 269, the noise-activated burglar alarm. So here we are with project number 269, the noise-activated burglar alarm. We're also going to be looking at project 270, the motor-activated burglar alarm, and 271, the light-activated burglar alarm with this same project. So there it is in the book, and here it is on the board. So we have our 3 volts switched by our slide switch here. Our alarm IC is providing output to our speaker there, being triggered using our PNP transistor, and our LED here gives a visual indication, which is fed by our music IC. So our music IC is acting as the trigger for this PNP transistor to activate our alarm IC. And the music IC gets triggered by our whistle chip here. So if we turn the circuit on, it starts making noise. We see our LED turn on. And then the circuit shuts off as the music IC finishes. And to restart it, you either make a loud noise around the whistle chip or you can just tap it. So it will restart any time a loud noise or a tap of the whistle chip is made. So that is how Project 269 is. Now Project 270 is the motor-activated burglar alarm. So with that, we're going to take this out. Take our whistle chip out of the equation. And we're going to now replace it with the motor. Put it up that way. I don't think polarity particularly matters, but we'll put it there anyway. So the circuit automatically started as soon as I connected the motor there because it allowed current to flow. Now, unlike the whistle chip, the motor activates the music IC as we've seen from previous projects where we had this setup where you just turn the motor. Because when you turn the motor, you induce a little bit of current through the coils in there, allowing a connection to take place. And that activates the music IC's trigger. So that's Project 270. Now 271 is the light-activated burglar alarm, and you can probably guess from that what we're going to be doing is we're going to use our photoresistor to control the music IC now. So that will put the photoresistor in the circuit there. Of course, for this I have to cover up the photoresistor. So like before, the circuit came on the moment I connected it. Now if I allow light into the photoresistor, unfortunately there's not enough light there, so let me use the little UV light from before. If I can get it to trigger here. I might need to use one of these. That's really hot. Okay, for some reason we do not have a trigger taking place here. Oh well. For some reason we are not getting the and now it decides to work. Actually, Okay. I guess the photoresistor is just acting a little finicky, but that's how that's supposed to work. So that's it for this set of Snap Circuits videos.